All right, so let's get back to integration by substitution. Let's take a look at this example. This is a really common question we've been seeing on the AP exam over the last several years. They give you an integral and they actually provide you with the substitution they want you to make. So here in this problem, they're asking you which of the following integrals is equal to our integral from 0 to 4 of x times root x squared plus 9 dx if you make the substitution u equals x squared plus 9. Okay, so in this example, we know we've got to use substitution. We're not even being asked to integrate. We're just being asked to bring this kind of into what I call U world, where everything is being written in terms of U, and find out which of these four integrals matches to our integral. So let's take a look at this on the tablet. So the idea here is just to go in and do your typical U substitution problem. So we're going to start this problem and we're going to say, okay, we're going to do the U they asked us to do. So I'm going to just copy this integral over. We're going to do the integral from 0 to 4 of x times the square root of x squared plus 9. Now, one thing I always do in my classes is I always stress the idea that the bounds have variables associated with them. This is really x equals 0. And this is really x equals 4. Now, most of the time that doesn't matter because it's just obvious we're dealing with a differential of dx, so we know that. But I like to just point that out, especially in a problem like this, because now we're going to do a substitution where u is equal to x squared plus 9. We're going to find that our du is going to be equal to 2x dx. So for all of you guys out there who wanted some review and use substitution, here we go. The idea is to bring our integral from what I call x world, where we do everything in terms of x, and we're going to bring it over here where everything's done in terms of u. So I refer to that as u world. So the way that works is you're allowed to bring over any function and any constant you want. So I'm going to start by bringing over the integral sign, because the integral sign is a function, so that can come over. And then I'm going to bring over the square root next, okay? Because that's a function. So we can bring that over, and we're going to bring that over as the square root, and we're just going to leave it open because right now what we've got to do is figure out how to bring over the rest. Everything else has an x in it. So now I've got to figure out how to bring over this x squared plus 9. So what I like to do is I like to kind of really emphasize this is my substitution box. This is how things are going to get changed from x to u's. So I'm going to bring this x squared plus 9 over to the box and be like, how do I encode that using u's? And they told us they wanted us to use that u was going to be equal to x squared plus 9. So u is going to go over here. So he's all checked off. At this point in time, the only two things I've got left are x and dx. So the question is, how do I handle this x and this dx? Well, they're both x's, so they got to go through our box. So the question that normally happens here is, do you want to bring them over together as one group, or do you want to do them separately? The good news is you don't need to answer that. You're going to go look at your box or your substitution, and you're going to go to that box and you'll be like, I need to find an x dx. If you can find an x dx in here, it's going to tell you how to bring them over together. So I come in here and I'm looking for x dx, and sure enough, there's x dx right there. So I'm going to isolate x dx. In other words, I'm going to solve this equation for x dx by getting rid of a multiplication by 2. I'm going to multiply both sides by 1/2. That means that when x dx comes into the box, it's going to enter as x dx, but it's going to leave as 1/2 du. And I'm going to put that 1/2 out in front, and I'm going to put that du at the end. Okay, so now we can look at our answers and we can start to see that we're starting to get an idea of what our final answer is going to be. And we see some similarities, especially with B and with D. We've got that 1/2 on the outside. I'm pretty confident about that. I've got the square root of u du in both of these. So the only question now is, what are we going to do about the bounds? Well, for those of you guys who just leave 0 to 4 there, you might think, well, 0 and 4 don't have an x in it, so I can just bring it over. But then you would fall for the trap and pick B, because that is an x value. It's x equals 0. It's x equals 4. So you've got to bring that through the box as well. So you've got to take x equals 0 over here to the box and say, hey, what happens when x equals 0? And in this case, what happens when x equals 4? Well, the place we're going to do that is the substitution that they gave us. What does u equal? So we were told that u is equal to x squared plus 9. So if x equals 4 and u equals x squared plus 9, well, that means that u is going to equal 4 squared plus 9. That's going to get us 16 plus 9 is 25. And that means our x equals 4 turns into u equals 25. This is going to be a top bound of u equals 25. We're going to have to do the exact same thing with this x equals 0. We're going to want to bring that into the box again. We're going to go to that u substitution they gave us. So now if x equals 0 and u equals x squared plus 9, Well, that tells us that u is going to equal 0 squared plus 9. And we're going to get that u is equal to 9 for the bottom bound. So now we know the bottom bound is u equals 9. This is what you have to remember. The bounds have to be substituted for as well. So you want to bring the bounds over just as much as you want to bring over the integrand and the differential. We now know that we're looking for a 1/2 root u du. We also know that the bounds have to be a bottom bound of 9 and a top bound of 25. We are going with answer C on this all the way. Okay, answer C is the answer we're looking for. Oh, I'm sorry, my mistake. I almost made a mistake. Answer D, my mistake. Again, it's a 1/2 out in front, not a 2. It's very easy to make that mistake. So you guys be careful when you're taking that exam tomorrow, okay? So it's 1/2 out front with a lower bound of 9 and an upper bound of 25. And of course, the square root of u du is what we're going to integrate. Very common question. Remember to bring your bounds over, okay? So the next example I want to look at with you guys, again, another common question on the AP exam. It's using properties of integrals. So this is a really common type thing where they give you a bunch of information about a bunch of different integrals, and you've got to figure out how to piece that all together to get information about a new integral. So what I encourage you to do is I encourage you to look at what you're trying to get. Okay, go straight to that. We're trying to get 1/2 the integral of 1 to 5 of g of x minus f of x. The given information, what I'm seeing is I've got some integrals from 1 to 12, and I've got an integral from 5 to 12. So first thing I want to do is I want to get an integral with g of x minus f of x in the same integral. That means they have to have the same bounds. I'm going to put these two integrals together and find out what kind of information I can get from that. So using those two integrals, what I'm going to do is I'm going to integrate from 1 to 12. And what I want to do is I want to start with this one because we've got that constant of 3 down there. Now, you guys know that that constant of 3 can be rewritten in the front as a 1/3, okay? And then once you know that, what's nice about this one is the integral from 1 to 12 of g of x dx. Well, with the 1/3 out here, it's equal to 5. But if you multiply both sides by 3, you're going to lose that 1/3. And when you lose that 1/3, this is actually going to turn to a 15. So now we know what g of x is doing from 1 to 12. We know what f of x is doing from 1 to 12. This is how we're going to be able to combine to get information about these two functions together. So I'm looking at where I want to go, and I want to get g of x minus f of x. So I'm going to set it up that way. So I'm going to go from 1 to 12, and I'm going to do g of x minus f of x as my integrand. And we know what that equals because we know that from 1 to 12, g of x is 15, and we know from 1 to 12, f of x is 14. So this is really just going to give us the answer 15 minus 14, which is equal to -1. So what we've got now is we've got this entire integral from 1 to 12. Now remember, they're asking us about 1 to 5. So we're just looking for part of this integral. But here's where the other piece of the information comes in. We know what's happening from 5 to 12. We know from 5 to 12 what's going on here. So what I want to do again is I want to rearrange this so the integrands match. All right, my integrand is the reverse of what I really want here. So using properties of integrals, I can rewrite this integral from 5 to 12, and I can change the direction of the integrand. I can make it f of x. Instead of f of x minus g of x, I can do g of x minus f of x. Now, remember, what that's going to do is it's going to basically put a -1 factor out in front. All I've done is I've factored out -1. It's still equal to -7. But now the good news is when I multiply both sides by -1, I now know this integrand from 5 to 12 is equal to 7. So putting these two pieces of information together, putting this one together with this one is going to be what we need to do. Because the integral from 1 to 12 of g of x minus f of x dx can be broken into two smaller integrals. It can be broken into starting at 1 and going to 5 of g of x minus f of x dx. We're keeping the exact same integrand. And now we can break that up from 1 to 5, and then we can continue by starting again from 5 and going to 12. And that's of g of x minus f of x dx. As long as we keep the integrand the same, we're all set. So now what have we computed already? Well, we know that this first integral, based on our work right here, is -1. We know that this second integral is kind of what we're after. That almost is a perfect match for what we're looking for. Yeah, there's a 1/2 there, but it's the exact same integral. So if we can find the integral, we can multiply that by 1/2 in a minute. So we're just going to keep this integral exactly the way it is, because that's actually what we're trying to find. And now we know that this integral, based on our previous work, is equal to +7. Okay, that's equal to +7. So from here, what are we going to do? We are now going to subtract 7 from both sides, and we're going to get this is equal to -8, and that's equal to the integral from 1 to 5 of g of x minus f of x dx. Well, now we go back to what we're after. What we want is half that amount. We're looking for half that amount because we've got the full integral from 1 to 5 here. This is telling us we want half of that. So all we have to do is go back here and multiply both sides by 1/2. And we multiply both sides by 1/2, what we end up finding is that this integral is actually equal to -4. Properties of integrals, very important problem. You're going to see that a lot in the AP exam. Let's take a look at another really common example that we see on the AP exam, especially over these last couple of years. Okay, and this one involves properties of integrals. So in a problem like that, like this, you're going to be given a bunch of information about some different integrals, and there's a way to connect them all. And your job is to figure out how do we combine these integrals to get the answer that we want. So the first thing I suggest that you do is you kind of look at the one you're after, because we're going to try and match this best we can. And what we notice in this is that we've got g of x first minus f of x, and we also have an integral from 1 to 5. So we know that we got to somehow combine this information up here to try to get g of x first minus f of x. Now, what I see right away is I've got two integrals about with bounds of 1 to 12. So that's going to be how I can put these two integrals together because they have the same bounds. So the first thing I'm going to do is I'm going to work with this integral of g of x, and I'm going to isolate the g of x. So what this is saying is I'm really integrating from 1 to 12, and I've got a 1/3 g of x, and it's equal to 5. So what I want to do is I want to take this equation, I want to multiply both sides by 5. If I multiply both sides, I'm sorry, multiply both sides by 3. If I multiply both sides by 3, I'll lose the 1/3 on this side, and then I'll multiply the 5 by 3 on the other side, and we'll get 15. So now we know how g of x and f of x act between 1 and 12. So I can start to build an integral that starts to look a little bit more like this. with g of x coming first and f of x coming second. So what I'm going to do now is I'm going to integrate from 1 to 12, and I'm going to put my g of x first minus my f of x. Because they have the same bounds in these given integrals, I can combine these two expressions, okay? So now what I know is that my integral of g of x is actually equal to 15. We just found that. And then my integral of f of x over these bounds is equal to 14. So I know this is going to give me 15 minus 14, which is positive 1. So now from here, what we've got to do is we've got to figure out how to go from our bounds of 1 to 12 to our bounds of 1 to 5. But properties of integrals say we can break up our integrals. So what we want to do is we can see that if we go from 1 to 5 and then 5 to 12, that's going to be the same as going from 1 to 12. So they've given me this integral from 5 to 12, but the problem with this integral is I've got the wrong order. I've got f of x minus g of x. So we got to rearrange this a little bit. What we're going to do in this integral is we're going to keep it from 5 to 12, but we're going to factor out a -1. And that's going to change the signs of the two terms in my integrand. So when I factor out that -1, I can write g of x first and f of x second. And that's exactly what we want to match it to the integral they're asking us about. This does not change the value of this integral. It's still -7. All I've done is factor out a -1. But what it does do is it tells me now if I multiply both sides by -1, this side will become positive and this side will become positive. So now I know that the integral from 5 to 12 of my integrand is equal to 7. So now I'm ready to piece together the integrals, because what I know is the integral from 1 to 12 of our integrand f of x, I'm sorry, g of x minus f of x dx is going to be equal to the integral from 1 to 5 of that same integrand f of x minus g, sorry, I keep saying it backwards, g of x minus f of x dx, and then plus the integral from 5 to 12 of g of x minus f of x dx. So because they all have the same integrand, we can break this up into pieces, okay? So what do we know? Well, we have shown that this first integral from 1 to 12 is equal to positive 1. We got that answer right there. So that's equal to positive 1. The second integral, this one from 1 to 5, that's really the one we're trying to learn about. That's the one the question's all about. So we're just going to learn as much as we can about this integral. And then we know this last integral from 5 to 12, well, that's the one we worked on up here. That's equal to positive 7. So from here, I am going to just subtract 7 from both sides. I'm going to end up with -6 equals the integral from 1 to 5 of g of x minus f of x dx. And that is almost exactly what I want. I've got the integrand in the right direction. I've got the right bounds. The only difference is I've got a 1/2 out in front. So now what I'm going to do is I'm just going to make use of very basic equation solving. I'm going to multiply both sides by 1/2. And when I multiply both sides by 1/2, I now have the exact integral they're asking us about, and it's equal to half of -6. That's going to give me the answer of -3. All right. So properties of integrals. Be prepared to be given some integrals and then using the properties of integrals. And that means breaking them up into bite-sized chunks like we did here, instead of going from 1 to 12, breaking that up from 1 to 5, then 5 to 12, multiplying, pulling out constants. Any of those kinds of integral skills can be used. Okay. So hopefully that will make sense. We're going to look at the next example. All right, Megan, thank you so much for all that help that you've been given all throughout the year. I know all the 5 of us students really appreciate you and the time that you've given and the expertise that you've lent them. We are now on the home stretch. We've got our last hour and a half before we wrap up today. And I'm going to take you to the end. And for our last hour and a half together, here's what we're going to be focusing on. We're going to be talking about, first of all, what I call a fundamental theorem of calculus free response question. I call it a super FRQ. It's going to be a little bit longer than you'll see on the exam, but what it's going to do is it's going to get you ready for every type of question that they might ask with that type of problem. Okay. Then we're going to turn our attention to separable differential equations. And then for the last half hour or so, we're just going to talk about common pitfalls to avoid on the exam and some test taking strategies and just some general things to be ready for tomorrow as you get ready to take that exam. Okay, so 90 minutes to go. Let's see how it goes. We're going to start right off with our Super FRQ question. It's going to be a problem where they give us a graph of G, but it's going to be an integral defined function where f equals some integral of G. Now, one thing that I like to do when I see these problems right away is I just like to look at this and see the geometry involved. There's all sorts of geometry as we look at this problem. So hopefully that you'll be ready for that. You'll be thinking about the geometry. We're going to see how that plays in. We're going to actually just jump right in and start answering these questions today. Okay, so here we go. Without any further ado. So in this first one, we're given, like I said, this graph of G, but the figure shows the graph G, which consists of 4 line segments in a semicircle. It's important that they tell you that because that means these are going to form the geometric shapes that they look like they're going to form. Okay, we can't always go by our eyesight. The AP exam, the College Board has to tell you so there can be no confusion. But that's what they're telling us, that these are the shapes that we think we see. And then we're told that we've got an integral from 0 to 15. And this problem is about a function, and it's going to surprise you. It's not G, it's about f, actually. And this is an integral defined function. So just some common things to keep in mind. When you've got an integral defined function, such as this one, where f of x is equal to an integral from 7, in this case, to x of the function g of t dt, some things to keep in mind. One thing that I promise you will come into play is you're going to need to take the derivative of this function. And the derivative of this function is going to be done using the fundamental theorem of calculus. If you did it out, what's going to happen is you're going to get a parent function, and then you're going to take the derivative of that parent function. And because this bound right here is x, it actually behaves very nicely. This becomes g of x. Okay, so this is going to be the derivative of f of x is equal to g of x. If this bound right here were not x, if it were anything else other than x, including a constant, you would want to use the chain rule when you take the derivative of that parent function. Okay, for the majority of the problems that we've seen, they're putting an x up there, so we're going to get f prime of x equals g of x. Okay, but again, if it's not an x, please do the fundamental theorem and use the chain rule to compute that. The next thing that you're usually going to need somewhere in the problem is you're going to need the second derivative. Well, f double prime of x is the second derivative of f. And now we know that's just going to be the derivative of g, so that's going to be g prime of x. I guarantee you that when you do this problem, these 3 equations are going to come into play. And when you turn in your exam, the person grading your exam, they are instructed to find where you wrote this down on the paper somewhere. They're going to be looking all over for it. It's going to be the first step into earning points into these types of problems. So please, when you do this problem, put it right up next to the graph, make it nice and big and clear so everybody can see it. Let the reader know that anytime you've got an integral defined function, you're going to get the derivative and the second derivative, again, by using the fundamental theorem. But if there's just an x up here, it works out just like you like. You're going to end up with g of x for the first derivative and g prime for the second derivative. Once you know that, you're ready to go. We can start working on this problem. We're just going to go piece by piece. It's kind of a long one because I wanted to show you every single type of problem they could ask you so you'd be ready for the exam. So in the first one, you're asked to find f of 14. F of 14 is using that integral defined function. That is the integral from 7 to 14 of g of t dt. This literally is a geometry problem because integrals can be thought of as geometric interpretations. So as I start to look at this one, what I notice about it is I've got a geometry problem and I'm looking for basically how to use this geometry starting at 7 and ending at 14. So starting at 7, ending at 14, here's what we're going to do. That means, let me just change colors so you'll be able to see a little bit easier. That means I'm going to start here at 7, and I am going to continue to integrate from 7 to 8, and then from 8 all the way to 14. That's all the way up to there. So we're talking about this region of the graph. Okay, that's what we're talking about. What I like to do right away is I like to just put the areas on my graph so I know what they are. So my first area here is a triangle with a base of 1 and a height of 2. 1/2 base times height is going to give me an area of 1 for this guy. When I come over here, I'm going to separate this into some pieces. That triangle is symmetric to the one I just saw, so that's also going to have an area of 1. As I continue to make my way across this shape, I could use a trapezoid, but for me, it's just a little bit easier to break this up into a rectangle and a triangle because I can compute that pretty quickly. The area of that rectangle, you can count the squares, or you could actually do base times height. Either way, you're going to get an area of 6 for that guy. And then as you continue, you've got this last triangle, which has got a base of 2 and a height of 2. So 1/2 of 2 times 2, that's going to be a region of 2 right there. So now that I know these areas, I am going to go and I'm going to compute this answer. And what I'm going to end up getting is, well, my G of t is, you got to be careful. It's positive for the first region and then it's negative for the next region. My D of t is positive for both, and that's because anytime the top bound is greater than the bottom bound, you get a positive dt. Some of you guys might think of that as integrating left to right, and when you integrate from left to the right, you're going in the positive direction. When you go right to left, you're actually going in the negative direction. What that does is it helps me figure out what my answer is going to be. It means this piece right here, I'm going to the right and I'm above the axis. That piece is going to be a positive piece. So my first piece of area is going to be positive. Then for the remainder, I'm still going to the right, but I'm below the axis. So the remainder of that is going to be negative results. Keeping that in mind, I can now find f of 14 by using the geometry. The first region right here is going to be given as positive 1. And then the next region is all going to be negative. So it's -1, -6, -2. That's going to get me -9. And I'm sorry, it's going to get me 9, but I've already taken care of the negative. So it's going to be 1 minus 9. That's going to get me a final answer of -8. So my first answer, f of 14, equals -8. Okay, and that is done by using the integral defined function and using geometry. If you see geometric shapes in a problem like this, you will use them every single time. So be prepared to label some areas and use that. So now for the second part, we're asked to do f prime of 14. Well, remember, up here, we've already identified what f prime is. So f prime of 14 is really the same as g of 14. Well, G is the graph. So really all we have to do is follow the graph of G and get to 14, which takes us right here. So at this point right here, the output of that graph is 0. So f prime of 14 is going to be the same as G of 14. That's going to give us an answer of 0. So there's our second answer for this one. And then the last answer we're looking for is f double prime of 14. But again, remember how we set this up in the beginning. F double prime is equal to G prime. So this is going to be G prime of 14. G prime of 14 refers to the slope of this graph. The derivative of G is the slope of this graph. So now we're looking for the slope in this region right here. Well, that's linear. That's why they're telling us we got line segments so we can read the linear graphs. Looking at that, we've got a rise of 1, a run of 1. This is going to be a slope of positive 1. So we know f double prime of 14 is equal to positive 1. The important things to take away from this example: number 1, if you see geometry, use geometry. It's going to be a part of the problem. Number 2, if you've got an integral defined function, please make sure you link how the function they give you, in this case G, is related to the function they're asking you about, in this case F. So these 3 statements become very important. You want to make sure you put those all over the paper so the reader knows that you've got them. Let's go ahead and now take a look at part B of this question. In part B of this question, we are asked this time to find the x-coordinates of the critical points of f on the interval from 0 to 15, and then classify them as a relative max, min, or neither. So the first thing we're going to do is we're going to start with critical points. A critical point is anywhere the derivative is equal to 0 or undefined. So since that's a critical point definition, we're going to find out where f, and we're talking about function f here. So where is f prime of x equal to 0? Where is f prime of x undefined? Well, f prime, again, according to our work from before, is equal to g of x. So we're looking for where g of x is 0 or where g of x is undefined. All right. Well, g of x is the graph. The nice thing about this graph is it is continuous. Because it's continuous, we're not going to get any undefined values for g. So we're really just looking for 0 values of g. So we're working on the open interval from 0 to 15. So the first place we see is 0, but we don't need to include that because it's an open interval. So we don't worry about the 0. And now we're just looking to find where are the zeros of this graph. We're going to get one right there at 8. As we continue this graph, we're going to find another one at 14. So what we know right now is that x equals 0 is a critical point and x equals 14 is a critical point. So now we've done the first part. We found the x coordinates. Second part, classify them and then justify. Well, what we know in this problem is that the graph of g is the same as the graph of f prime. So as we look at this problem, what we're seeing is this graph is positive before 8 and it's negative after 8. So what we can say about this is that f prime changes from positive to negative. That means we're going to have a relative maximum. Because anytime your slope changes from positive to negative, you change from your function changes from increasing to decreasing, and that means you have a relative maximum. When we go and we look at 14, what we're going to find out is that f prime changes from negative to positive there. So because f prime changes from negative to positive, we've got a relative min. So for question B, those are the answers we need. That would get us full credit for the exam. We've identified the x coordinates and we've also classified them. Okay. Let's move on to part C in this problem. In part C, we're asking about where does f have an inflection point. So what you need to remember about an inflection point. Inflection point, the definition of an inflection point is a point where the second derivative changes sign. So this is going to be a point where, in this case, f double prime of x changes signs. But we're given a graph of g, which again is the graph of f prime. I'm sorry, graph of g is f prime. So we want to know, where does the second derivative change signs? Well, another way to say the second derivative changes signs is to say that f prime changes from increasing to decreasing, or vice versa, decreasing to increasing. So what we're looking for on this now is a place where this graph is going to change direction, basically, where it's going to stop going up and start going down, or vice versa. So as we trace this graph out, it's increasing the entire way until 5, and then it begins its decreasing. That tells us that x equals 5 is going to be an inflection point because we change directions from going up. In other words, the graph is increasing to going down. Okay, so that definitely is going to be an inflection point right here. All right. Now we're looking for where it stops going down and changes at a point to going up. Well, it stops going down here, but it doesn't start increasing. It's flat. So this is not a point where we change from increasing to decreasing. This function does not do that here. And as a matter of fact, it doesn't do it here either because it's 0 the entire way in between. So this is really a sticky point for a lot of students, but you got to remember is because there's not a single point where the graph changes from increasing to decreasing. When I say the graph, I mean the graph of f prime of x. There is no inflection point in this region. So the only place we have an inflection point is at x equals 5. If we want to justify this, you're going to be tempted to say the second derivative changes signs. But we're not given the second derivative. We're given the first derivative. We're given f prime as a graph of g. So the way we want to say this is because, and here we go, we're linking g to f prime because our graph g, which is really f prime, changes from increasing to decreasing at x equals 5. And that's going to be what you need because when you say the derivative changes from increasing to decreasing, you're saying the second derivative changes from positive to negative, and that's a change in signs of f double prime. Okay, so always make your justifications go back to the given information. This is a given information about g, which is really f prime. My justification has to be f prime. That's why you don't see me talking about f double prime changing signs here, because I'm going back to what they gave me. That's how you earn the justification point every time. Okay, so now in the next one, very similar question, but this time they're asking you, where is f increasing and where is it also concave down? Okay, so let me see if I can just re-highlight that for us. Where is it increasing and concave down? So you want to take this on by saying, okay, what does increasing mean? What does concave down mean in terms of f? Well, increasing means the function derivative is positive, so we got f double prime, I'm sorry, f prime is positive, so that's what we're looking for. And we're also saying where the second derivative is negative, okay? But remember, we're talking about g, which is the same as f prime. Notice I'm writing that in every single part of this. So really what we're doing is we're saying, where is g of x greater than 0? Okay, and where is g prime of x less than 0, which means g of x decreasing. So we're looking for any places where g of x is greater than 0. In this case, that means g of x is above the x-axis. So we're looking for where we're above the x-axis and decreasing. So in this whole region, we're above the x-axis. And in this region, we're above the x-axis. So those are potentials. But the second part is you also have to be decreasing. The only place I see that function decreasing is in this region. I just highlighted in yellow. Okay. In this region, we're increasing. The function g is increasing. Same thing over here. So this is the answer we're looking for. Where is this function both increasing and concave down? This guy is going to be increasing on that interval and concave down on that interval. So it seems it starts at 5 and it ends at 8. Okay, so the answer to our question here is 5, and then we're going to go all the way um, until 8. Now, I personally would want to say that we've got to take a break at 7 just for a second. Okay, so from 5 to 7, but then again, start at 7 and go to 8. And the reason I like that answer instead of just 7 to 8 is because at this point right here, what we know about this is that G prime is actually undefined. The slope there is undefined. That is a cusp, or some of you might call it a corner. It's an abrupt change in the slope. Since the G prime is undefined, to me, my way of answering that says it's not less than 0, it's not greater than 0, it's not equal to 0. It's the fourth option, it's undefined. So I feel like we have to have a break there and go from 5 to 7, and then again from 7 to 8. So there's the answer that I would give for this particular problem. Okay, but again, the key here is making sure you relate F and G. So I should write a really quick sentence here for my justification. Why am I going to justify this the way I have? Well, I'm going to say this because now I'm going to talk about F prime here. So why is F increasing? Because F prime of X, which equals G of X, always make the link, is, well, I want to say positive, and I want to say decreasing. Because that's how I knew to pick it, because it was above the axis and it was decreasing. So there's my justification for that answer. Let's keep going because there's so many different questions they can ask you with this fundamental theorem. So here we go. We're looking at part E in this one. And in part E, they're asking us to find the absolute maximum of F. Now, this is a problem. Whenever you see these words, absolute maximum, what jumps into my head right away is this thing called the candidates test, okay? You want to go and you want to make a candidates test. And the candidates test is all about the following. Candidates test. It's looking at your endpoints and your critical points as the candidates. And once you've identified all the endpoints and critical points, you just see which one gets you the highest or the lowest value. In this case, it's going to be highest. We're looking for the absolute maximum. So what we want to do is we want to identify all the endpoints and all the critical points. So it's very useful in this type of problem to go and make a table, because the idea is you're going to just compare inputs and outputs to find your best value. So we want to find the candidates for F. So the candidates are the endpoints and the critical points. So we're looking for where F prime of X is equal to 0, But remember, f is the same as g. We keep saying that over and over again. So we're saying where is g equal to 0? Those are going to be our critical points. And our endpoints are just going to be given by the problem. We're told our endpoints are 0 and 15. So one candidate is automatically 0. So there's our first candidate, 0. Now our next candidate is going to come where we find a critical point, which means where f prime is 0, which means where this graph is equal to 0. So this is actually a critical point and an endpoint. As we keep moving along the graph, the next critical point we see is right here at 8. So we're going to make 8 a candidate. The next critical point we see comes down is right here at 14. So what I'm going to do is I am just going to copy this table really quickly so you guys don't have to switch back and forth from screen to screen. So the next candidate, we got 8 for that last one. Our next candidate is 14. And our last candidate is going to be 15. It's going to be that endpoint. So here's our job. Our job is to go now and find the outputs for each of these guys. Well, that means using our function f. Well, f of whatever I plug in is equal to the integral from 7 to that value of the input of g of t dt, which means we are going to have ourselves a lot of geometry going on in this problem. We're going to start computing integrals all the way back to 7 and all the way to 15. We're going to be computing integrals up and down this particular function. So what I'm going to do to make my life a lot easier is I am going to break this up into some shapes to start with. And let's just break this up like this. Obviously, we've got a nice triangle before 3. So our first shape I'm going to do is that triangle. Then I'm going to do a cut at 7 to get that shape. Then I'm going to do another one here at 9 because I'm just breaking this up into shapes I can easily identify. Okay. And now I'm just going to go through and I'm going to label these shapes with their appropriate areas as found by using geometry. So that last one I just did, I'm going to cut that semicircle at the top. So here we go. Our first shape is this triangle right here. That's got a base of 3 and a height of 2. That's going to give us a area of base of 3, height of 2, half of 6. That's going to be 3. So that is our region right there. The next shape I see, I'm going to color coordinate here, is this rectangle right here. So I'm going to go and I'm going to compute the area of that rectangle. I could use base times height, or I could also just count the blocks, whatever's easiest. So no matter what you do there, you're going to get an area of 8 for that rectangle. The next thing we're going to look at is that semicircle up there. And that semicircle is half of pi r squared. So I'm going to go and I'm going to compute half of pi r squared for that. And when I do that, when I do that, sorry about that. Let me just redo that. Little technical difficulty with my marker. Let's redo that. So when I find that area, it's going to be half of pi r squared. Okay. So that's going to be pi over 2 times the radius squared. Well, the radius here is 2, so that's going to give me 4. So that answer is going to be 2 pi for that shape right there. You may remember from earlier in this problem, we already found the area of that triangle. That triangle is an area of 1. We also said the area of the triangle below was 1 because those were symmetrical. We also found the area of this rectangle from before. The area of this rectangle we said was 6. And again, doing base times height for that. This last triangle, or not, I shouldn't say the last triangle, but this next triangle, we found that area already. We said that the area of that triangle, let's see here, is going to be half base times height. So half 2 times 2, so that's going to be 4. And then the very last triangle that we've got is this guy all the way at the end, and that's going to be a area of 1/2. I'll just write that over there so we can see it a little better, okay? So I find it much easier just to go through and label everything, because now what I'm going to do is I'm going to start by finding out the outputs for these values, okay? So the first value I'm going to do is I'm going to do 0. So I'm going back to the integral defined function right here. I'm plugging in 0. When I plug in 0, that's like saying I'm starting here at 7, and now I'm going all the way back to 0 in this direction. What that means is all of the areas that are above the x-axis are going to be counted as a negative because they're normally positive, but we're going backwards. So since we're going from right to left, it's the reverse of what we think, which means all of these above the x-axis, they're positive heights, but they're negative bases because we're going to the left. So we're going to get these three shapes put together, but it's going to be negative for all of it. So 3 and 8 is going to give me 11. So that's actually going to be negative 11, and then I'm going to have a minus 2 pi. So my output for 0 is negative 11 minus 2 pi. The next one I'm going to do is I'm now going to start at 7 again, but this time my new input is going to be 8. Okay, so I want to know what happens for this point now. So I'm going to plug in 8. So this time I'm starting at 7 and I'm just going to 8. So I'm above the axis and I'm going to the right. Positive and positive means my result is going to be positive, and I'm just going to use the area that's given by that triangle right there. So that's going to be positive 1. Okay, I don't need to write the positive. I'm just stressing that we're going to the right and we're above the axis. So that's positive 1. So now I'm going to do the same thing, but I'm going to do it for 14. Well, this time when I go and I substitute and plug 14 in, I'm going to get f of 14 is the integral from 7 to 14. Now, I've already done some of this work because now I'm still starting at 7, but I'm going all the way to 14. So this time I want to integrate going all the way to 14. That means I'm still going to get this 1 as a positive, but I'm going to get all these as negatives because I'm going to the right, but we're below. So it's going to be positive 1, but then it's going to be minus the rest of those. So when I subtract the 1, the 6, and the 4, that's actually going to be minus, I'm sorry, that's not 4. My mistake. That's not a 4. My mistake. That's not a 4. Let's go back and redo that. That's 2 by 2. So it's half of 4. That's going to be a 2 there. I apologize for that. So now, glad I caught that. So now when I go and I do this, it's going to be a positive 1 here from this triangle, but it's going to be a negative 9 from these three. So it's going to be positive 1 minus 9. That's going to give us an answer of negative 8. All right. And then for the last one, all I'm going to do is start at the same place, 7, but I'm going to go all the way to 15. So all I'm really doing is just taking this and extending it one more shape. So I'm going to get the same answer I got before. I'm going to get all that negative 8 back, but I've got to add that last shape, which is plus 1/2. Okay, so it's going to be negative 8 plus 1/2. That's going to give me negative 15/2. So now these were my 4 candidates, 0, 8, 14, and 15. The question is, which is the absolute maximum? Well, I just look and see which one has the highest y value. That value is negative, that value is negative, that value is negative. There we go. There's our absolute maximum. So find the absolute maximum value. The absolute maximum value is, now be careful on this, it's the value. They want the output. We've got to say the absolute maximum value is positive 1. A very common mistake is for students to write x equals 8. That's not the output, that's the input. They want the output. So the absolute maximum value is 1. Now here is the beauty of the candidates test. When it says justify for the candidates test problem, this is the justification. You don't have to write anything else. This works for your justification. And that's the beauty of it. So you can just write absolute maximum value and you can be done. So my advice to you on this is to label your areas ahead of time. And that way you can just go and literally read the areas off as you're jumping around. Be a little more careful about your areas than I was there. That's an area of 2. And use the candidates test because therefore, if you do it, you don't have to provide any more written justification. Okay. Let's take a look at the next type of problem they might ask in this Super FRQ. All right. So in this next one, they're introducing a brand new function. And this function now is this h of x function. So we look at this and they're saying find h prime of 5. Well, take a derivative. That's all it's saying. So we're going to take the derivative both sides. This is going to be h prime of x. When I take the derivative of the other side, the 1/3 is a constant, so it's just going to come along for the ride. And now I've got to use the chain rule on this. So the derivative of the outside is f prime of something. Copy that inside, and now take the derivative of that inside to complete the chain rule. And what we end up with is h prime equals 2/3 times f prime of 2x. Now again, as we've done in every other problem, f prime is really equal to g. So that's going to tell us we've got 2/3 of g of 2x. When we go to do h prime of 5, that's saying to substitute in 5 for x, so that's 2/3 g, and this is going to be 2 times 5 from down here, so it's actually going to be g of 10. So now, final answer, we're getting really close. All we've got to do is find out what g of 10 is. Well, g of 10 can be read from this graph. So there's g of 8, g9, g of 10. So g of 10 is right there. That is the input 10 and the output -2. So we're going to put a -2 in for this. And that tells us that h prime of 5 is going to equal -4/3. -4/3. Okay, so that's what we're looking for here. So again, it's going back to the graph every single time, but we're still using our calculus. Don't forget about your chain rules, or you're always want to be on the lookout for using the chain rule. So the next example actually takes this function, this 1/3 f of 2x, and asks another question. Okay, so let's just remember that h of x equals 1/3 f of 2x. And now in this one, they're asking us to find the equation of the line that is tangent to h at x equals 7. My students have been programmed to always start this by writing down the point slope form of the equation. They know they're looking for 3 blanks. We're looking for an x value here. We're looking for the, and usually it's called x equals a. We're looking for the output when we plug in a for that one. We're looking for the derivative when we plug in a for that one. But in this example, be careful, because we're not finding the equation of the tangent line to f, we're finding it to h. So let's go back and let's be really specific about this. Let's say we're finding h of, well, our a value in this case is 7. So let's do this the right way. It's going to be 7 for that value, h of 7 for this value, h prime of 7 for that value. So in goes the 7, and now I'm finding h of 7 and h prime of 7. Well, h of 7 is given by our function up here. It's 1/3 of f of 14. Okay, that's going to be h of 7, 1/3 f of 14. Well, to find f of 14, that would mean going back to this guy and saying f of 14 is equal to the integral from 7 to 14 of g of t dt. Well, if we're doing the integral from 7 to 14, again, we kind of have already done this a couple of times. We know that this value here was 1, and this value here was 1. We know that going to 12 gave us 6 more, and we know that going to 14 was half base times height, half of 2 times 2, which is 2. So as we go and do this integral from 7 to 14, we're going to be moving left to right. So the 1's going to be positive, the other one's going to be negative, the 6 is going to be negative, and the 2 is going to be negative. So when we work that all out, we're going to get -8 for this example here. Okay, we're going to get -8 for f of 14, but remember, it's 1/3 times that answer. So that's -8/3. So there's our h of 7. It's going to be -8/3. So we're going to put 8/3 in that blank, and we're going to make that a negative, which makes it positive. So now the last thing to do in this problem is find h prime of 7. But remember what h prime was. Let's go back up here. Let's recompute that. That's going to be h prime of x is equal to, it was 1/3, and then the chain rule went into effect. So it was f prime of 2x all times 2. That was 2/3 f prime of 2x. So h prime of 7 is going to be 2/3 f prime of 2 times 7, which is 14. Well, when you go to find f prime, remember, this is the graph of g, okay? And g is equal to f prime. So I'm looking for f prime of 14. Read it from the graph. We're talking about this value right here. So f prime of 14 is equal to 0. So that actually means we've got a 0 slope or a horizontal line. I would tell my students just to leave this problem exactly the way it is. This is perfectly acceptable. A lot of people will want to say that this side goes to 0, so we've got y by itself being y equals -8/3. Of course, that's an acceptable answer. But you don't get extra credit for that, so I would just leave it right like this, okay? So let's go now and take a look at the very last part of this free response question. We're finally getting to the end. So in this one, you are asked, that tangent line we just computed, if we use it to approximate h of 2.1, would the result be an over approximation or an under approximation? Okay. Well, tangent lines and approximations, what you got to remember is that if you have a function, let's just draw this down here out of the way. If you have a function that looks like this, okay, and you have a tangent line approximation to it, what that's going to mean is you're touching at that one value. So this would be touching just like this, okay? So this is our tangent line approximation. Well, the red values are the approximate values, and the blue values are the actual values. Well, in this case, the approximate values are always less than the actual values because they're beneath it. They're underneath. The only place they're not underneath is at the point of tangency. That's the one place they're the same. So for a shape like this, the approximate is less than the actual. How would we get it to work the other way around? The shape would have to look like this. If you have a shape that looks like this guy, and now you draw your tangent line wherever you want it. Well, in this case, the red are the approximate, and the blue are the actual. And in this case, the approximate are greater than the actual. I hope by looking at this, you're starting to see what's going to cause this to happen. It comes down to the concavity. If you're concave up, your approximate values are less than your actual values because your tangent line will be below. If you're concave down, your approximate values will be greater than your actual values because your shape, your tangent line is above and your shape is below. So if you're asked to ever find out whether or not a tangent line approximation is an over or an under approximation, that is code for find the second derivative and check the concavity of the function. So what we want to do here is we want to find the concavity of h. So we know h of x is equal to what do we say it was equal to? It was equal to that function 1/3 f of 2x. We've also seen that h prime was equal to 2/3 f prime of 2x. Well, we got to go one step further. We got to do h double prime of x, and that's going to be equal to 2/3. This time it's going to be the second derivative of that inside function times the derivative of that inside function. So h double prime of x is equal to 4/3 f double prime of 2x. And the question is, what is the concavity at and around x equals 2.1? So the concavity here, that's going to be looking at the concavity really kind of like this, h double prime of 2.1. That's 4/3 f double prime of 2 times 2.1, which is about 4.2. So we're looking around x equals 4 in the graph of f to find out what's going on. Well, remember, the graph of g is really f prime. So f double prime is the slope of g. Well, when we look around 4, what we're talking about is we're talking about looking around this region right here. Well, although I can't compute it directly, I do see that that slope is going to be positive everywhere in that region. So what we know is that h double prime is going to be, h double prime of 2 is going to be greater than 0, which means that h is concave up in this region. And if h is concave up, that means the tangent line approximation, well, remember, if you're concave up, you're below. So the tangent line approximation is going to be an under approximation. This particular example takes you through all the different questions that I've seen over the last 20 years or so that talk about using the fundamental theorem of calculus in conjunction with an integral defined function and using geometry to get the answers. I hope this really makes a lot of sense to you guys. Personally, I'm telling my students I'm quite confident they're going to see a problem like this. So I hope you get one tomorrow and that you guys are able to crush it. Okay.